Welcome, ladies and gentlemen. So what I'd like to do is show you how to evaluate the composition of a function or two functions, and one being the inverse of the function. Now, basically, remember when we're evaluating for the inverse of a function, basically what we're trying to do is find the angle, right? So the inverse of a function, for instance, let's use the unit circle. You know, if I had sine inverse of I don't know. Of sine inverse, I'm like drawing a blank. Let's do of square root of 2 over 2. Right? Well, the angle that produces, square root of 2 over 2, is going to be pi over 4. Now, pi over 4 is unique because of the range. So the range is very important. So we're always going to have to, whenever we're dealing with the inverse, we cannot forget the ranges of our three functions of sine, cosine, and tangent. So basically, if you want to think about it one way, the cosine, I'm going to do the first one kind of slow, and then I'll kind of speed up the other ones. So basically, the sine inverse of 4 over 5th really represents an angle, right? Because when we take the inverse, the trigonometric inverse of a value, that's going to produce an angle. So really, let's say this. So in reality, the sine inverse of 4 over 5 equals an angle. That's really what we're evaluating for. And we can evaluate the cosine of an angle, right? We can always find the cosine. But I say, you know, what is the cosine of 1/2? I'm sorry. What is the cosine of pi halves? Right? The cosine of pi halves, you just go and look at your unit circle. And you say, oh, cosine of pi halves, that's going to be 0, right? So we can evaluate for angles, all right? So if I have sine inverse of 4/5 equals to theta, well, how can I really kind of make this sense? How can I take the cosine of that? So what we can do is, well, I can take the sine of both sides. Just like you were solving an equation. If you take the sine of both sides, the sine of sine inverse, those undo each other. So we're left with 4/5 equals sine inverse of, or sine of theta. Now, how can we take this? If we know sine of theta is equal to 4/5, how can that help us find theta, right? Again, we're trying to figure out theta because we can take the cosine of theta, right? We can take the cosine of an angle. But the problem is we still don't know what the angle is. But what's helpful now about this is we know that the sine of theta is equal to 4/5. We know what the sine represents. 4/5 is not a point that's on the unit circle, right? I couldn't take this on the unit circle and say, oh, the angle is equal to is here. That's not one of the common points that we see in the unit circle with a given angle that we're familiar with. So when we don't know what points on the unit circle, one thing we can always look into is using a triangle. Now, notice that 4 and 5. Now remember, so what I did is I kind of drew part of the unit circle here. And what I did was I only drew the part of the unit circle, though, that is within the range of sine. Because remember, the range of sine is between negative pi halves and pi halves. Now, sine is opposite over hypotenuse, right? Well, since the hypotenuse is always positive. So since 4 is positive, we know that my triangle has to be in the first quadrant. It can't be in the second quadrant because then the y part would be negative. So we have 4 over 5, OK? So now that's what theta represents. The sine of theta represents 4 over 5, right? So if we want to figure out the cosine of that theta, then all we need to do is figure out what the x is. Because remember, cosine of an angle is adjacent over hypotenuse. So you could either use the Pythagorean theorem, or you could know your Pythagorean triples and identify this as 3. So therefore, the cosine of this theta, which is produced by the sine inverse of 4/5, is just going to be 3/5 adjacent over hypotenuse. All right, so now let's go ahead and actually, you know, I'm going to skip over 3. I'm going to do the 2 positive ones first, and then I'll get into the 2 negatives. Now, I'm not going to go through this whole ordeal here of figuring out the theta. Basically, what I want you to understand is we need to take the sine of this, right? Well, this, again, represents an angle. So how does tangent inverse represent an angle? Again, 7 over 24. Remember, tangent of an angle represents opposite over adjacent, right? So if the opposite and the adjacent side are both positive, tangent is only positive in the first and the third quadrant. But remember, just like sine, tangent only has a range of your inverse function, because we are taking the inverse of tangent. Inverse tangent only has a range in the first and the fourth quadrant. So I can only draw a triangle in the first and the fourth quadrant. Well, so therefore, my tangent in the negative quadrant can't be. This has to be in the first quadrant. So I'm going to draw a triangle in the first quadrant. Theta is going to be opposite over adjacent. And again, ladies and gentlemen, you can use the Pythagorean theorem. Seven squared, I don't know why there's a line over it. 7 squared plus, or 24 squared plus 7 squared equals your hypotenuse squared. 7 squared plus 24 squared equals 625. So then you end up getting 625 equals your hypotenuse squared. You take the square root, and what you get is your hypotenuse is equal to 25. And hypotenuse is always going to be positive. OK, so now we know that theta produced 7 over 24, or at least the inverse tangent of 7 over 24 produced a triangle with theta. Then we found our remaining point because we need to figure out sine. Because sine of theta, which this represents here, the theta, sine of theta is opposite over adjacent, or opposite over hypotenuse.
The front office is now empty if you want to lock that for us. Thank you.
So we have opposite over adjacent, which is 7 over 25. And there we go. All right, let's get to these two because they're locking up and it's during the summer, so I got to get going here. The next one here is I have tangent times cosine inverse of -5 over 13. Now in this case, you can see that we have something that's negative. So now remember cosine, let's see here. Now from cosine, we remember that cosine has an inverse cosine has a range of 0 to 2 pi. So when can I write a triangle that's negative? Now remember, 13 is the hypotenuse. That's always positive. So when 5 is negative, that means my triangle has to look like this. OK, so that's going to be -5 over 13. Still, my opposite is still going to be positive. Again, knowing either using the Pythagorean theorem or using your Pythagorean triples, you will get a value of 12. OK? So now that you know that you have a value of 12, you can now evaluate the tangent of this angle. Tangent is going to be opposite over adjacent, which will be 12/15, or negative 12 over 5. OK, last one. That is a -12 over 13. Now remember, going back into sine. Sine is only a part of in the first and the second quadrant. Since this is now negative, that means 13 has to be positive. That means my negative, I'm going to use a red here. That means this now, I have to create an angle here where this is -12 and my hypotenuse is 13. It's still going to be, my x value is still going to be negative, but now I know my triangle is going to be a -12, and that's a positive, oops, no. That's a 13. Now again, going back to using my Pythagorean identities here, that is going to be 5 because it still has to be in the first quadrant, right? Sine is either in the first and the third quadrant. So even though this is negative, it just puts it in the third quadrant. But your x value is still going to be positive. It's never going to be on the negative. X is never going to be negative. So now, remember, tangent is opposite over adjacent. Here's my angle, opposite over adjacent. So for the cotangent, it's going to be adjacent over opposite. So that's going to give me a -5 over 12. So there you go, ladies and gentlemen. That is how you evaluate for the inverse of two trigonometric functions, or I'm sorry, the composition of a trigonometric function and the inverse of a trigonometric function. Thanks.